We'll now give an introduction to the matrix inverse and what it means. Before we define the matrix inverse, we need to define the identity matrix, which we'll denote by I sub n, where the n determines the size. This thing does need to be square, so it'll be an n by n. And the idea of the identity matrix is any matrix times the identity should be itself. In addition, I2 should look like 1, 0, 0, 1. If I do I3, I have 1, 0, 0, 0, 1, 0, 0, 0, 1. And in general, IN follows this pattern. I need ones on the main diagonal and zeros everywhere else. Now that we know what the identity matrix is, we'll have a theorem regarding this. If we have a square n by n matrix A, and we'll say its reduced row echelon form will represent by R, then either R has a row of zeros or it's equal to the identity matrix. As long as we start with a square matrix, this will happen. We'll either have a row of zeros or we'll have the identity matrix once we've reduced it. We'll now prove this. If we have this matrix R that's a square matrix, it either has n pivots or less than that. It can't have more since there are no more rows or columns. If we have n pivots, that means there is going to be a leading entry in each row. And since reduced row echelon form requires those leading entries to be ones with zeros both above and below them, we're only forced to have the identity matrix. It's the only one we can have of that form. If there are fewer than n pivot positions, then there has to be one column without a pivot. Since each pivot column also corresponds to a row, this means that we have a row without a leading entry, since we're square. And this is specifically because we're square. If we weren't, then we could have a matrix that had fewer rows than columns, and this wouldn't come up. But because we're square, this means that we have a row that doesn't have a leading entry. And since there's a row without a leading entry, that means it's all zeros. So we do have a row of zeros. We'll now actually define a matrix inverse. The matrix inverse of a matrix A is any matrix C such that AC is equal to I and CA is equal to I. If the inverse of a matrix exists, we call it invertible. So invertible just means it exists. It is possible that it doesn't exist, in which case we call it singular. So singular means that this inverse doesn't exist. We'll now give a theorem that involves these inverses. The inverse of any given matrix A is going to be unique. There's only one inverse, if it exists. And if that happens, then we denote it by this a to the negative 1, which is read A inverse. And we'll now look at proving this. Anytime we want to prove that something's unique, we suppose it's not. We'll suppose that both B and C are inverses. Then I know that AB is equal to AC, and both of these are equal to the identity by the definition of an inverse. I'm going to multiply on the left by B on both sides of the equation, and then I'll move around my parentheses and make this BA times B is equal to BA times C. Since B is an inverse, BA is the identity. And the identity times the matrix is just that matrix. So that I have B is equal to C. Therefore, this thing is unique. Before we actually talk about how to find the inverse, we need to define an elementary matrix. And an elementary matrix is any matrix that is formed by performing a single row operation on our identity matrix. Some examples. Well, if I have my identity matrix, I could switch 2 rows. In this case, I'd switch the second and third row. And so this is an elementary matrix. In addition, I could multiply a row by a number. In this case, I multiplied the second row by 7. I can also add a multiple of one row to another. Here, I added -3 row 1 plus row 2. So these are all elementary matrices. We'll now talk about some of the properties of these elementary matrices. We start by supposing we have this matrix E that results from performing some row operation on our identity matrix. Therefore, E is an elementary matrix. Then if I multiply E by a matrix, EA, this is the matrix that results from performing that same row operation on A. This means essentially multiplying by an elementary matrix is the same thing as performing a row operation. Another theorem that is relating to elementary matrices. We have that every elementary matrix has an inverse, and that inverse is also an elementary matrix. And this comes from the fact that row operations are reversible. So the inverse would be the reverse row operation. We have 2 more. The first one, we have that every matrix A can actually be decomposed as a product of elementary matrices and the reduced row echelon form of our matrix A. If we denote this reduced row echelon form of matrix A by R, then we know that A reduces to this matrix R through a sequence of row operations. We also know that every row operation can be represented by an elementary matrix, in particular a product of elementary matrices. Therefore, we know that we have EP, EP minus 1, all the way down E2, E1A is equal to my reduced row echelon form, where these E matrices are just the row operations that I need to get from A to R. We also know that each one of these elementary matrices is invertible, and the inverse is also an elementary matrix. So if I start multiplying both sides by the inverses, I get that A is E1 inverse, E2 inverse, and we'll keep going up to EP inverse times R, which then gives us what we wanted. And then we have one last theorem. Our last theorem states that if A is an n by n invertible matrix, then its reduced row echelon form is actually the identity matrix. This, combined with my last theorem, means that if it's invertible, it can just be a product of elementary matrices, since that last R would just be the identity matrix.